If you have worked with databases, especially relational databases, or if you have read about them or heard about them, then most likely you have heard the word normalization. So what is normalization? What does it do? Why do we do it? How do we do it? And what would happen if we don't do that? In this video, I will talk in depth about normalization and what it means. Hello and welcome. My name is Elhelw. I made a video about database design and talking about the different steps of database design. And one of these steps was logical design, which included a step about normalization. And I said that I was going to make a separate video about that, so here we are. So what is normalization? The formal definition would be something along the lines of normalization is a technique that is used to split the data into multiple tables in order to minimize data redundancy and improve data integrity. What a mouthful. What does that mean? Let's try to kind of like explain it in more simple terms. What is redundancy and integrity, right? Redundancy means the repetition of data. Data that is repeated multiple times, like the same data repeated multiple times. Why is that a bad thing? Aside from the obvious thing of just using more space, the main problem with the redundancy is that it adds the probability of making mistakes. It adds this likelihood of making an error that would end up in data that is inconsistent or data that is contradictory. What does that look like? So let me show an example here that has two rows, both with the same customer ID, but they have different birth dates. In this table, we did not define a primary key, so this is just the data in some regular columns. What's the problem with this data? The problem is that we have two rows with the same customer ID but different birth dates. This means that implicitly it's almost like we have a customer that has two birth dates at the same time. So it's inconsistent data. The data is contradicting itself. When we have data like this, it means that we cannot trust the data in the database because we don't know which one of these is true. Why did this happen? Because we don't have a primary key, so we were able to add two rows with the same ID that may have different information. So this is one of the issues that we can deal with. So as I said earlier, normalization as a process, it intends to minimize this redundancy, which leads to inconsistent data. We would never have a situation in a normalized table that has two rows with the same ID but different information. The problems that arise, which normalization tries to address, can be classified into three main categories. We call them the insertion anomaly, the deletion anomaly, and the update anomaly. In simpler terms, these are issues that happen as you insert, update, or delete data. We'll get into examples of what these look like as we explain the process of normalization. So just remember these terms for now, but we'll get into those later. All right, so how does normalization try to reduce this redundancy, right? You may have heard about the term normal forms. What are these? These are a series of criteria or a series of conditions that we check to see how good or bad the database design is. If you think about the spectrum of being from horrible design that's super dangerous and prone to all these problems to the other side of being amazing design, super safe, doesn't allow any of these things to happen, think of it as something like this. From this side to that side, there are different stages. And this is what we call the normal forms. So you start with the first normal form, second normal form, third, and so on. We represent each of them by 1 NF means first normal form, and so forth. So if your design satisfies first normal form, that's a step in the right direction. If it satisfies the second normal form, that's even better. If it satisfies the third, that's even better, and so on. So the higher up you go in the normal forms, the more safe your design is, and the less prone it is to some of the anomalies we mentioned earlier. Each of these normal forms already implies that the previous ones are satisfied. So like when you're checking your design, first you check the first normal form. If it's not satisfied, then you have to take some action to make your data or you make your design comply with the first normal form. And then you check the second normal form. Second normal form, the first condition is going to be that it has to satisfy the first normal form first, and then there will be additional conditions on top of that. So we'll see all of that in detail. We're going to talk about the various normal forms. I will try to explain them in simpler terms, might be a little bit different from what you would find in like the formal literature. So this description or the examples that I'm going to use here are more kind of like, practical examples. Knowing these or following the definitions in this video will allow you to have a very good design for your database. I may not get into some of the like more subtlety or like some of the rare cases. If you want to know more about these, please feel free to go look for some other references or other material that goes into the normal forms in depth. If you finish this video, you would have sufficient information to have a really good database design. So let's start. Let's look at this table. So we want to store information about some teams and their members. Suppose we have two teams, front-end team and back-end team, and each team has a bunch of people. One way to do this would be to store it in something like this. Have two columns, team column, member column, and then in the members column, just list all the members in that team. Right off the bat, I'm going to tell you this table does not satisfy first normal form. Why is that? Because first normal form does not allow multi-valued cells or multi-valued attributes. So if you have a multi-valued attribute, you're not even in first normal form. Why is this a problem? The problem is because it's very difficult to query this data. You have data like represented as a string or whatever it is. It's very hard to query it. You cannot find a particular member of the team. You cannot do any operations. If, let's say, Anna wants to switch teams from the front end to the back end team, how do we find Anna in the members, and how do we delete it from the front end team? We have to do like some string processing, so it's not like super straightforward. We have to do some additional processing on top of what we can do with SQL. So first normal form tries to make the querying the data easier and more straightforward. So the solution would be to split the members into individual rows. So each row would have one of these members and what team this member is in. So the table would look like this. And again, about the example of switching teams, if Anna wants to switch from the front end to the back end team, all we want to do here is just update this value from front end to back end, and we're done. And if we want to get all the members of a certain team, like basically what we had before in the initial representation, all we need to do is just have a SQL query that selects all the members where team equals, back end, for example, and this will give us, Anna, Jenny, and Bob. It might also return Bob, Anna, and Jenny, or any other order. So data could be returned in any specific order, doesn't matter. Or does it? Are there situations where I actually care about the order? There are. Let's say, for example, that I want to return the team members in their order of seniority, or in the order of when they joined the team. One may try to do that by saying, okay, I'm going to represent or store the data in the order in which people join the team. So I'm going to rename this column to call it member by seniority. I'm going to add the data in the order in which people join this team. It's going to be stored in that order in the table. So the first person will be the most senior, the last person will be the least senior. And when I retrieve this data, it's going to come to me back in that order. This is actually not true, and this is not first normal form. Why is that? Because when I query the data, now I have this expectation in my mind that the row order is conveying some information, like the row order is conveying the seniority of these employees. So I'm querying the data and I have this expectation that the data is going to return in that same order. It may, so I might get Jenny, Anna, and Bob from the back-end team, but I also may get Anna, Bob, and Jenny. So then I will think that Anna is the most senior person, which is not true. So then there's an inconsistency here. Why did this inconsistency happen? Because I used the row order to convey some information. In relational databases, we should not do that. So this is one of the conditions of first normal form, is that we never use the row order to convey any information. If we want to represent this information, we have to represent it explicitly. So if I want to represent the seniority or the order of the people by joining the team, I can simply add another column that has this order. So 1 means like first person joined the team, 2 second person, and so on. So this way I can easily get that data in the order that I want. Even better would be to store the actual join date. Why? Because if I store the number like 1, 2, 3, 4, 5, and a person leaves, then I have a gap, and then the next person comes in, so I will add to the end. So as people come and go, there will be gaps, and then maybe these gaps will have some issues. But having the join date is something that is specific to the person, doesn't really leave gaps or anything like that, and I can easily order by that as well. So if I want to get all the people from the backend team ordered by seniority, I can do a query like this, and it will return the data that I want in the order that I want. So far we've seen two conditions for being in first normal form. First condition is don't have multivalued attributes. Second condition is do not use the implicit row order to convey information. There are other conditions, so we're going to look at the third condition right now. Let's say this table has an additional row that looks like this. Front end, Tom, and this date. This is pretty much like a duplicate of the second row. This is a problem. The fact that we have this duplicate, first of all, this is not also a first normal form. First normal form says that we cannot have duplicates in the table, duplicate tuples or duplicate rows. Why is this an issue? We have two possibilities. One possibility is that we actually have two people with the same name who joined the team on the same day. So this data could be valid. But the problem in that case would be that there is no way to distinguish. There's no way to refer to one or the other because they both have the exact same data. So that's a problem. The other possibility, which is probably more likely, is that there was a data entry problem and we ended up inserting the same row twice. This means that we have duplicate data, which means that we might end up updating one of them, for example, and then we will have inconsistencies. So either way, it's a problem, which is why first normal form says that we cannot have duplicate rows in any table. Well, how do we fix it? The easiest solution is define a primary key. So if we define a primary key here, let's say we add an employee ID column, this prevents that problem from happening. So if we go back to the two possibilities that we mentioned, it's either going to be like if there are actually two people with the same name that joined in the same day, each of them will have a different ID. So then we have a different way to distinguish them and we have a different way to refer to each of them. If it was a data entry problem and we attempted to insert the same row twice, then we're going to try to insert the same ID twice, in which case the system will complain and will not accept having the primary key value, inserted twice. So adding a primary key protects us from both these issues. So to guarantee that you don't have duplicate rows, always define a primary key. All right, so let's summarize the first normal form again. So the first normal form, we said the conditions are you do not have multi-valued attributes, you cannot use the row order to convey information, and you always define a primary key to avoid having duplicate rows. Aside from these three conditions, there are actually two more conditions, but those two conditions are usually taken care of by the database system, so we usually don't need to worry about them. One of them is no mixing data types in a particular column, so we cannot store integers and strings and dates and so on in the same column, which is something the database usually takes care of. Once you define the column with a particular type, it will make sure that everything that you insert satisfies this type. The second thing is that you cannot have multiple columns in the table with the same name. Again, this is something that the database will enforce anyway. You cannot define a table that has multiple columns with the same name. So these conditions are usually already satisfied, but I am including them here for completeness. Let's see another example of a table and see how do we make it follow the first normal form. Suppose we want to store student information and course information. So for each student, we want to store what courses they're enrolled in and what's their, let's say, midterm scores in that course, right? So we can represent the data kind of like conceptually like this. We have a bunch of students. Each student has some course and score information. Like we said, we cannot store multi-valued attributes, so we need to split them into separate rows. So the table will look like this. So student ID, course, and the score. Each row has a single value. We don't have any row order implicit information there. And now we need to define the primary key. So as we said, each row depends on the student and the course, right? So the primary key here would be both attributes together. That defines the primary key. So for each combination of student and course, you only have one unique row that has the score of that student in this particular course. So that said, this table now satisfies the first normal form. Okay, let's go to the next normal form, the second. Now, starting from that table that we just saw, let's say that we want to also store the instructor for each course. So one way to do this would be to add an instructor column here that says, the math course that is taken by student 01 is taught by Bob. The econ course is taught by Anna, and so on. So now we have these instructor information in the table. This table is still in first normal form, right? So it still doesn't have any row order information. It doesn't have multi-values, and it has a primary key. But this is not a good design, and it introduces problems. Why is that? Let's see. Suppose that student 03 decides to drop the chemistry course. They don't want to be enrolled in that course anymore. How do we represent that in the data? We would just delete that row, the row that has student 03 and chemistry. The problem with that is that now we don't know who teaches the chemistry course because we deleted also the instructor information. This is what we refer to as the deletion anomaly. So the deletion anomaly means that we were deleting something, but as we were doing that, we also deleted something else unintentionally. We were trying to delete the association of student 03 with the chemistry course, but while doing that, we also deleted who is the teacher for this course. So that's a problem. Another problem is, let's say we want to change the instructor of the math course to John instead of Bob. So technically, we would have to go over this table and change all the occurrences of Bob where they teach math and change that to John. There might be lots of rows that have that information, so it would be very easy to miss one of those, or there might be like an error or something or bug in the system, and the system crashes when we have done some of these updates, but not all of them. So we might end up with a situation where we change that first row that has math, now the instructor is John, but there is another row at the bottom that is still pointing to Bob. This is called an update anomaly. Now we have two rows that both have the math course, but one of them says math is taught by John, the other says math is taught by Bob. So this is inconsistent data, and this is a problem. Another problem is, what if we want to add a new course? Let's say we're going to offer an English course taught by Nancy. We cannot insert that course into this table because no students have been enrolled in it yet. And the key here is, the primary key is student ID and course. So as long as there are no students, we cannot insert this data in the table. So this data basically doesn't exist in the database. So we have no record that says that we have this English course taught by Nancy. This is an insertion anomaly. We cannot insert this information. Why do we have these problems? Why does adding the instructor column introduce all these problems? The reason is because this column basically means that this table is not in second normal form. Like I said, it's still in first normal form, but it's not in second normal form. Second normal form addresses the relationship between the primary key and all the non-key attributes. In our case here, the primary key is student ID and course, and the non-key attributes are score and instructor, so all the attributes that are not part of the primary key. What is the relationship between those? Second normal form says, for something to be in second normal form, first it has to satisfy the first normal form, which we do, and then each non-key attribute must depend on the entire primary key. Okay, what does that mean, and is that satisfied or not? Like I said, we have two non-key attributes here, score and instructor. Let's look at score. What does score depend on? As we said, score depends on the combination of student and course. Like student 01 in course math, they got this score. So score depends on both. So we can represent that as this, saying that score depends on both student ID and course. This is how we denote it. This is called a functional dependency. So score depends on the entire primary key. So that's good. This satisfies the condition. What about the instructor? Instructor depends on the course only. It has nothing to do with the student. Knowing the course should tell us who the instructor is. So we will say that, instructor is dependent on course. Course is not the primary key. Course is part of the primary key. So this means that the condition is not satisfied for this attribute, and hence the table is not in second normal form. How do we make this table, or how do we change the design so that we are satisfying the second normal form? All we need to do in this case is split this into two tables. So one table would be the initial student course table that has student and course and score. And then we have a new table that has the course information, including the instructor. It can have also multiple other information, like things about the textbook, or like, the website link, or whatever it is that you want to add about the course. So now with this new design, let's look at the dependencies. Instructor depends on course ID, and course ID is the entire primary key for the first table, so that's good. And then for the second table, score depends on student and course. Both are the entire primary key of the second table, so now this satisfies second normal form. Now, if we look at the anomalies that we discussed before, do they still apply, or are they fixed? Now, if you remember, if we delete, if student 3 wants to drop chemistry, right, then we would delete that row from this table that says SO3 and chemistry. That's fine. It does not delete the fact that chemistry is taught by Julia, so that it's still stored in the course table. If we want to change the instructor of math to be, John instead of Bob, we have to only update it once in the course table. We don't have duplicates of that information, so that's also solved. If we want to add a new course, English taught by Nancy, we can do that. We just add a row in the course table, even though there are no students enrolled in that course. So that's also solved by this new design. So you can see now how going from first normal form to second normal form fixes a bunch of issues. All right, let's move on to the next one. If we look at that course table that we just created, the one that has the course and the instructor, right? Suppose that we want to store the instructor phone numbers. So we're going to add the phone numbers here as well. So now we have for each course the instructor name and their phone number. Is this in second normal form? Yeah. Both pieces of information, the non-key attributes, they both depend on the course ID. What problems might we have here? Let's say that we decide that math, instead of being taught by Bob, we're going to switch, and Tom is going to teach it instead. So we're going to change Bob to Tom. But we forgot to update the phone number, which may happen because maybe you don't know that the phone numbers are associated with certain people. So now we have two entries with Tom, but with different phone numbers. So this is an inconsistency. And that happened because of the update, so that's an update anomaly. Another problem, let's say we want to add a new instructor that is not teaching any courses yet. We cannot add that instructor in this table because, again, the primary key is the course ID, so they have to be teaching at least one course to exist in this table. So this is an insertion anomaly. We cannot insert this new professor. If we delete the chemistry course, right? So we want to say that this course is not offered anymore. We want to delete this course. But this will also delete Julia and her phone number. So we don't know what Julia's phone number is, even though she still works in our school. Basically, this deleted all her existence. So that's a deletion anomaly. So why did this happen? Like I said, this table is still in second normal form, right? Because both instructor and phone, they both depend on course ID. However, the question now is, how do they depend on course ID, right? Knowing the course, we know the instructor, so that's a direct dependency. However, for the phone, it doesn't depend directly on course ID. It actually depends on the instructor, which depends on the course ID. So like there's one hop, it's a transitive dependency. Which means that the direct dependency is actually between phone and instructor. This is something that is not allowed in third normal form. Let's look at the conditions for the third normal form. It says it must satisfy second normal form. As we said, every form must satisfy whatever is before it. Plus, no non-key attribute should be dependent on another non-key attribute. Here, phone and instructor are both non-key attributes, and one of them is dependent on the other. Hence, this is not in third normal form. Okay, how do we fix this? Simply, we just split that into a different table. So we say that, okay, we're going to have an instructor table. This table will have all the instructor information. So let's say the name is going to be the ID in this case, and we're going to have a phone number. You could also add additional information like their email, their address, their website, whatever information you want about the instructor is going to be in the instructor table. All that information is dependent on the instructor ID. And then the course table will just have the course ID and the instructor name. Let's look at the dependencies again. Now, instructor depends on course ID, which is the primary key. There is no dependencies between two non-key columns. So now this satisfies third normal form, and the anomalies that we talked about are gone. Let's try again. Like if we want to change the instructor for the math course, we just change it once. We don't need to worry about the phone number. The phone number is stored in a different table. If we want to add a new instructor, we just add into the instructor table, even if they don't have any courses associated with them yet. If we want to delete a course, we can delete that from the course table. The instructor information for that course will still be preserved in the instructor table. So all the anomalies are gone now that we are in 3NF. Next, I want to talk about another normal form that is called Boyce-Codd normal form. This is not the fourth. This is still kind of like a little bit after the third. So usually donated by BCNF, Boyce-Codd normal form. This is seen as an upgrade to the third normal form. So sometimes it's written at 3.5 NF. So it's like somewhere between the third and the fourth. I'm not going to get too much into it. Just let's see the difference between BCNF and 3NF. So 3NF said must satisfy second normal form and no non-key attribute is dependent on another non-key attribute. Boyce-Codd takes this a step further and says that no attribute is dependent on non-key attributes. So not just the non-key attributes that we're checking, but we're checking all the attributes. None of them can depend on non-key attributes. In most cases, having something in third normal form will also have it in BCNF. There are some rare cases where the table will be in third normal form but not satisfy BCNF, but those are very rare, and most people never encounter those. So I'm not going to get into those in this video, but if you are interested, you can find plenty of material about those specific cases, how they would happen. Up to this point, so we've seen first, second, third, and BCNF. With these conditions, like if you have all of these satisfied in your database, then your database is already in a pretty good shape. We're still going to talk about the fourth and the fifth normal forms, but those are kind of like a little bit more advanced, so not many people try to get into that while they're designing a database, but we're going to talk about them anyway. So let's look at the fourth normal form. Before we get into what it means, let's look at this example. Suppose we have a clothing store. We sell different types of clothing. We sell jeans, shorts, t-shirts, and we have a list of the available colors and sizes for each type of clothing. So jeans, we have blue and black colors are available, and we also, the available sizes are large and medium. For shorts, the available colors are green and gray, and the available sizes are small and extra small, and so on. We want to represent this as a database. So one would create a table, put item, color, and size, and put all the different combinations. So for jeans, for example, you have 2 colors and 2 sizes. So we have 4 combinations, black large, black medium, blue large, blue medium. And the same thing for every other item. So yeah, this captures pretty much the information that we have. And the key here is item, color, and size. Now, suppose that we want to add another color for t-shirts. We're going to say that, okay, actually now t-shirts are also going to be available in the color white. So what do? How do we add this information? The way we added the information, we consider all the different combinations, right? So white in t-shirts should also be available in large and small. So we need to add these 2 rows. T-shirt, white, large, t-shirt, white, small. Obviously, it takes some mental exercise to figure out what rows to add, right? and you might miss something. So we might add just one row and forget to add the other one. But now the information will be inconsistent because now you don't have anywhere that expresses that you have white small t-shirts. Why is this, why did this happen? If we look at the information we had in the beginning, we will see that looking at every product, every item, like jeans, for example, we said that jeans has these available sizes and it has these available colors. So basically there's some kind of dependency from the item type to the sizes and to the colors. There is no dependency between the colors and the sizes, right? Like those are independent. But knowing the product item, it will tell us what are the available colors and what are the available sizes. So we call that a multi-valued dependency. Knowing one value for the item tells us multiple values for the size and multiple values for the color. So we denote that in this way. We have multi-value dependency from item to color, and we have this kind of double-headed arrow, and the same thing from item to size. When we came up with this table, we kind of created almost an association between the color and the size, which introduced the problem that we have. Let's go to the fourth normal form definition or criteria. Fourth normal form must satisfy BCNF. And also it says that every non-trivial multi-valued dependency must depend on the key. There's a lot to unpack here. What is a non-trivial multi-valued dependency? We already know what a multi-valued dependency is. So item to color or item to size, those are multi-valued dependencies. What's a trivial or a non-trivial one? A multi-valued dependency from x to y would be trivial if y is a subset of x. So if you could say you have a dependency from item and color to color, like knowing the item and color, I know the color, obviously. This is called a trivial multi-valued dependency. The other one is if x and y, like both sides of the dependency, together they're pretty much like all the attributes in the table. This is also called a trivial multi-valued dependency. So let's look at the two dependencies that we have. Are they trivial or not? Item is not a superset of color. Color is not a subset of item, right? Size is not a subset of item. So this part is not the case. Do item and color constitute all the columns in the table? No. Are item and size all the columns in the table? No. So then those two multi-valued dependencies are not trivial. So going back to the condition, every non-trivial multi-valued dependency, so those two that we have, they must depend on the key. In our case, they depend on the item attribute. The item attribute is not the key. The item attribute is part of the key. Hence, this condition does not hold, so this is not in fourth normal form. How do we fix it? How do we change it so that it is in fourth normal form? Simple case, go back to the information that we already had. We had information from item to color and from item to size. So we can split this into two tables. A table that maps between item and color, and a table that maps from item to size. This will capture all the information that we have. If we want information to combine them, we can combine these tables. Now let's look at the dependencies again. We said from item to color and item to size. Now for each of these tables, these dependencies are now trivial because the columns are pretty much all the columns in the table. So then we don't need to worry about that condition anymore. So this is in fourth normal form. Now, going back to our example, if we want to add another available color for t-shirts, white, all we have to do here is add one row to the item and color table. So t-shirt, white, we don't need to worry about the sizes. We don't need to worry about how many rows we want to add. Just one row from t-shirt to white, and that's it. So this is what fourth normal form looks like. Let's go to the next one, the fifth normal form. Fifth normal form is complicated. The higher up you go in the normal form stack, the more complicated they get. This one is usually not the easiest to explain or to understand, so I'm going to try to explain it in simple terms as much as possible. The conditions are, as usual, first condition, you must satisfy 4NF. The second condition says there must be no join dependencies. What does that mean? A table will have a join dependency if this table can be the result of joining smaller tables without data loss. So if you look at a table, a big table, and you say, hey, this table is actually, I can split it into multiple tables such that if I join those tables, I'll get that original table again without any, missing rows or extra rows or anything like that. Then that initial table has a join dependency, and that table would not be in fifth normal form. Let's see an example. Let's say we have multiple pizza brands, P1, P2, P3. I could have found more fancy names, but I was lazy, so let's just stick with those. And let's say each one of them offers, different flavors. So P1 offers cheese pizza, veggie pizza, mushroom pizza. P2 brand has cheese or chicken, and so on. So that's some information that we know. Now we have a couple of customers, and they have some preferences. So Anna says she likes brands P2 and P3, and also she likes, in general, flavors chicken and mushroom, while Tom prefers brands P1 and P2 and likes cheese, veggie, and chicken pizzas. Now, what does that information look like in the database? So one would say, okay, let's create this table that has the customer, brand, and flavor, and put the information in there. So for Anna, for example, Anna likes P2 and P3, and she also likes chicken and mushroom. So let's see, does P2 offer chicken and mushroom? P2 offers chicken. So we're going to put a row for Anna, P2, and chicken. P3 offers both chicken and mushroom. So we're going to add 2 rows for P3. So Anna, P3, chicken, Anna, P3, mushroom. And the same thing for Tom. Notice that as I was doing this, I was kind of like doing some mental exercises to kind of like figure out which rows to add, right? So it's like almost I'm doing a join in my head. So, okay, now we have this table. What happens if, let's say, Tom starts to like the brand P3 as well? So how do we update our table? We're going to have to do that mental gymnastics again and say, okay, so Tom now likes P3. And Tom likes cheese, veggie, and chicken. Does P3 offer these 3? Well, P3 offers cheese, mushroom, and chicken. So cheese and chicken are in common. So we're going to add 2 rows. 1 Tom P3 and cheese, 1 Tom P3 and chicken. So that's a lot of processing in my head to get this. It's very easy to miss some information. If you're doing this automatically, you might have some bug in your code that will miss some information. So that insertion may not insert all the data that you want. Clearly, this is not the best way to represent this data. So if you go back to the basics, what information do we know? We know 3 pieces of information. We know for each brand what flavor it produces. That's 1. We know for each customer what brands they prefer. That's 2. And we know for each customer what flavors they like. That's 3. So that table that we have here is basically the join of those 3 pieces of information. So the solution to get our data to be fifth normal form compliant is to split this into the individual pieces. So we will have 3 tables, a table that maps the brand to the flavor, table that maps the customer to the brand, and then customer to the flavor. So now we have all these 3. If we join these 3 tables, we'll get the initial table that we have. So this means that the initial table had a join dependency. The initial table was not in fifth normal form. These tables are in fifth normal form because we cannot decompose them any further. Now, let's look at the example that we just saw as well. Tom now starts to like P3. We don't need to do any mental gymnastics. All we have to do here is just insert 1 row that says Tom likes P3 in that customer brand table. And that's it. Once we do the join, that join will take care of everything else and it will figure out what rows to output. So the idea is to just put the information that we have in here and let the database system do the rest using the operations that it has. And this is what the fifth normal form is all about. All right, so this gets to the end of the video. So let's summarize everything we talked about. We talked about normalization as a way to minimize redundancy and improve data integrity. As we mentioned, normalization helps us avoid things like insertion anomalies, update anomalies, and deletion anomalies. We also talked about the various normal forms, 1 through 5, plus BCNF. Each normal form has to satisfy everything that comes before it, in addition to some new criteria that it looks at. And the higher up that you go in the normal form stack, the better design that you have in general. Hopefully this was helpful, and hopefully this kind of makes sense in terms of how normal forms are checked and why they're important. Please let me know if you have any questions. Put them in the comments. Hit the like button if you like this video. Share it with others. Subscribe to the channel to get all the updates. And with that, I will see you in the next video. Thank you for watching.